presenting. I'll be just giving an introduction and a little work in this area. Also the methodology we're going to follow, and also an overview on the SNN components, whereas Malinta will give you information on the biological background of the spiking neural network and the VHDL implementation. Spiking neural models are quite different than the existing neural networks. They are considered as the third gen neural networks because compared to the existing ones, they integrate the notion of time. Here, neurons communicate using spikes or electric spikes or pulses, and compared to the existing neural networks, there's a new concept where input signals are encoded and then fed into the network. Again, the output spikes are also decoded and then the output is identified. So our project will focus on implementing the LIF neuron. It's a type of leaky integrate and fire neuron. There are many other types of neurons as well, but we'll be focusing on the LIF neuron and the MNIST dataset. These are our objectives. We'll be implementing the LIF neuron and synapse models to update the weights, initially on MATLAB, and we will do that to obtain the parameters of the model. We'll be also using the MNIST dataset, which is 28 by 20, which contains 28 by 28 images. Therefore, in the spiking neural network, the input layer will contain 784 or 28 by 28 input neurons, and then the hidden layer will contain 46 hidden units. Output layer will contain only 3 neurons, where we will just try to classify only three digits, and we will be using the rate coding mechanism. Basically, if we take an image, we have input neurons for each pixel. So what we do is, in rate coding mechanism, we take the pixel value of that, the gray value of that particular pixel, and then we will be converting it to a rate, and that is what will be fed to the neural network. And we'll also be implementing backpropagation for the SNN. These parts are the backpropagation, that part is on MATLAB, whereas after obtaining that model, we'll be verifying or testing using the VHDL code. This is just some related work in the area. There are several minimalist SNNs where they have used the MNIST dataset, and it was around 3 layers, and it's actually quite memory efficient and requires a minimal amount of time, this particular SNN architecture. And also we have to get an idea on the fundamentals of the encoding the input signals, and again decoding. Again, the backpropagation mechanism for the SNNs are also in the area, and finally we found a paper on comparison of FPGA implementations using the IRIS dataset, and compared to the MLP and RBF neural networks, they give comparable performance. This is the methodology we're going to follow. In MATLAB, we'll be implementing to learn the network parameters, and then we'll be doing the validation. This is an equation that can be used to this V means it's the rate, and in a range we define the max and min. According to the gray value, we'll be identifying rates for the particular pixels, and this is the network configuration, whereas the neural encoding decoding part, the encoding part is what's mentioned here, and the decoding means I'll explain it in the next slides. As you can see in the end, the decoding part, we are trying to identify the input pattern. So the time to first spike decoder, what it does is, out of the 3 output neurons, whatever neuron emits the first spike, that's what is that's what the input pattern is given, and Martha will cover the rest.
Thank you, Sabra. For this circuit, we can consider this circuit as the electrical representation of the of a biological neuron, whereas in a we are considering about the LIF neuron in this project. So LIF means weak integrate and fire. So in this represent this schematic shows three major components of biological neuron. First, we can think this input current as the current that is flowing from synapse or any other external input to the neuron, and then this whole circuit as the membrane part of the neuron, and then this outgoing arrow as the axon of the neuron that is flowing current to the outside neuron. So since we are focusing about the weak integrate part, this resistor here, it acts as the leakage, the component that is responsible for the leakage part, and then this capacitor here, it acts as the membrane of the neuron where it stores charge that is coming from the input current. And so once the input current is flowing into the neuron, some part of the current is flowing through the R, and then some part of the current is flowing through the capacitor, and the capacitor is charging with the current with the time being. And then once the membrane potential, which is the charge of this capacitor, reaches this value V, the neuron emits a spike, and then it discharges. So the charge of this capacitor, or the charge of the membrane potential, it reaches a value that is called the resting potential. The resting potential is not zero. It is provided by this biological battery here. And once the spike is emitted, the neuron falls into a refractory period where it does not do anything, and then it starts charging again. So if you follow the Ohm's law and the Coulomb's law, we can come up with this equation. This is a first order differential equation, and then if we solve that, we can come up with this equation where we have this statement for the membrane potential. So this is how the membrane potential changes with the incoming current to the neuron. And here we have a current that is flowing into the neuron, and then membrane potential is initially at the resting potential, and then it increases with the time, and once the current becomes zero, because due to the leakage, the membrane potential gradually reaches a resting potential. And here we have some sort of a larger electrical signal that is coming to the neuron, and then here, because of this larger value, it reaches this threshold value, and then it emits a spike, and then it goes on and on like that. So that was the neuron model, and here we have the synapse model implementation. What basically the synapse does is it converts incoming spike train into a flowing current according to this equation. Basically what happens here is we have a spike here, and then synapse convert it into this current here. With the time being, the effect of this spike gradually reduces with the time being until it meets another spike, and then it generates this current as this graph shows. So this is the implementation schematic that we came up with for the neuron model. So this is the same equation that we saw in the neuron model equation that we used Ohm's law and Coulomb's law. Right. So in here, because once we plug everything into the neural network, we can have input current that is flowing into the neuron from either from a lot of synapse connections, or either from bias current. So we can write this IT as we can disintegrate this IT into these two components here, and then we have a component in the neuron inside the neuron implementation where it does the multiply and adding of these values, and then it does. We have another adder which adds it with the bias current, and then a multiplier, and we have a division operator here, and then we have an exponential part which calculates this part, and we actually, to be honest, it's here that we learn that floating point operation and the division could be hugely computationally heavy. So for the exponential part, what we saw in the existing implementation, what they have done here is in which they are keeping a lookup table for the existing values inside the brackets. So we can use that lookup table here. And for these parts here, since these values are coming from the these values are initially coming from rates, we can solely create those rates to be integers, and then once we put that multiply and then we multiply all of these things together, and then we add and compare this with this whole part with the threshold potential, and then if it exceeds the threshold potential, we emit a spike. So this is basically the neuron implementation, and I will be responsible for this part. And then we have the synapse model. If this is the same equation that we saw in the synapse model equation, and basically we did some math, and then this S minus T part is actually some coming from a equation called the Dirac's data equation. So if you actually integrate that part using the Dirac data properties, then you will get this equation finally. So this is the equation that we plan to implement in the synapse implementation, where we have a counter which accounts for keeping the record of all the most recent spikes that came into the neuron, came into the synapse, and then we have a register where it keeps records of the spike in times, the firing times of each of the neurons, each of the spikes, that most recent spikes, and then we have this combination block where it does addition, division, and exponential parts, and we have a component which executes this combinational block iteratively for in the range of 0 and the number of spikes in the synapse so far, and then it stores the value that is coming from this combination box, and then it calculates the current from here. So this is what we came up with so far. So to be honest, as I said, it's here that we learned that floating point calculation could be quite difficult, quite heavy here. So what we plan, so our first thought is we looked in some of the GitHub implementations of floating point calculations. So we thought of plugging that libraries into our PHDL code, or otherwise we are looking for some other suggestions. Thank you very much.
Go back to the objective slides. This is a very good project, maybe the best so far, because you have the initiative to look for a new type of neural network other than external net or binary connection. And this is also a very important neural network named the spiking neural network. And also this is a very ambitious project. If you cannot finish this project, please first to implement the leaky integrate fire model.
Right.
I think that's a more important model.
Right.
And maybe you can do the training by software, but please do the testing by hardware first.
Yeah, sure.
And what data set will you use? Data set to do the testing will you use?
You mean the training part?
The data set.
The data set.
Data set MNIST.
Okay, that's good. Okay.
For MNIST, we have just wrote a simple MATLAB code for identifying 6, 7, and 9 digits, and we with the single layer neural network where we have 46 hidden neurons, we could get about more than 90% accuracy. So that is why we said that this is 46, the number 46, that is where it came from.
Okay. Thank you.